Welcome back. We're continuing our discussion on electron pair geometry. So what if we have sulfur tetrafluoride? Okay, good place to test your knowledge of naming. So it's sulfur tetrafluoride, right? Good. And so if consistent with what we've been doing, okay, the element that's least in count goes at the center, so I'm just going to put my sulfur, and sulfur is a 6A, right? So that means it's got 6 valence electrons, right? And fluorine is a 7A, right? So it's got 7 valence electron, right? Right. That's for each fluorine. There's 4 of them. So first go ahead and evenly distribute your 6 electrons on the sulfur, and then let's get a different color for our fluorines. So we got fluorine with 7 electrons. Remember when I said whenever you have 3, 4, 5 onwards, you got to split the number of valence electrons into pairs of 2, so I got 3 pairs of 2 and an odd electron, right? So let me erase it so I can position it a little bit closer. I did that just to show you. So I'm gonna get my fluorine. So this is my fluorine. Again, where you start is entirely arbitrary. You don't always have to start because I started here. I mean, don't get bogged down with those kind of details, because then you're adding own pressure on yourself to always get this right, and these things are very arbitrary. All right, just make sure you have 7 electrons. Now we're left with a lone pair of electrons, right? So let's go get another color and connect these bonds. So a blue and a black, blue and a black, blue and a black, blue and a black, right? So that leaves us with AX4E, right? Now keep in mind with electron pair geometry, right? Now sulfur, except the only element that does not have an electronegativity values are the noble gases, which is why we couldn't do it for xenon. But you know what, if you calculate the electronegativity, I can tell you, I'm not going to actually calculate the value, but I can tell you from my experience, fluorine is definitely more electronegative of the two. So I'm going to go get my maybe a red. Okay, so sulfur is more, fluorine's more electronegative than sulfur. You could actually do it and determine which one's more of the electronegativity table is included in the weekly course shell, and then there we go, right? But like I said, it's kind of like, imagine that all the arrows are pushed down kind of because of the lone pair, so the net effect is it's only acting in one direction, which is why we say something is polar. Now if this not had been there, then that would be a different story, which is what we will see when we discuss molecular geometry in week 5. So this is how you demonstrate the bonds themselves are polar covalent, right? If you take the difference, I believe it's between 0.6 and 1.7, right? We say that is polar covalent, right? Polar covalent. So with that said, the bonds themselves are polar covalent as well, and then the molecule as a whole is polar. We have looked at cases, where the molecule, the bonds themselves may be polar covalent, but then the molecule as a whole will be nonpolar. If you want, I will come back and touch that example which was in the previous video, just as we are talking about. So the electron pair geometry is, we treat the E as a bond, so it's technically AX5, so AX4E is here, which is same as, so it's trigonal bipyramidal. Okay. All right. So that's pretty much all the examples. It's much easier to work with electron pair geometry than it is to work with molecular geometry, which we will see. It takes a little bit of memorization, but again, you don't need to memorize everything. There's only like 4 or 5 names that you have to memorize. So while we're on the topic, remember I said that you can have a molecule that may have polar covalent bonds, but the molecule itself may be non-polar. And the example I showed you all was AlCl3. Now Al is in group 3A. Okay, so that means it's got 3 valence electron, and Cl is in group 7A, so it's got 7 valence electron, right? And as always, the element that's least in count goes at the center, and you can evenly distribute the 3. Even if you did, that is no big deal. Similarly, you go get your another color, perhaps maybe a pink. So each chlorine, we've done enough examples, so I feel more confident going straight to this. Chlorine's got 7, and you got to split it into pairs of 2, right? Right? So that means you go get your bond, say blue, connect the pink and the black, pink and the black, pink and the black, right? Now if you do go look at the electronegativity value that I gave you earlier in the videos, it's also in the core shell, you'll notice that clearly chlorine is more electronegative than aluminum, right? You can use this or partial positive. This is partial negative, right? We only do this for polar covalence, right? Right. So again, same deal. This or that, right? Same thing. The tail is positive, the head is negative, right? You can use one of the 3. We see that each of this bond is polar covalent, but the molecule itself is non-polar, right? And I explained why, and I'll explain it again here. So it's A, right? 1 central atom, 3 outer atoms. No. So it's trigonal planar, right? What that is really it's on the plane. Okay, any molecule that's perfectly planar, you don't need to, again, I don't expect you to do this, but what happens here is, let me get a different color quickly. Okay, this is happening, this is my F and this is my Cl and this is my Al, right? So there's 2 that are happening this way and there's 1 that's happening this way. So what essentially happens is these 2 have a collective going up and this one is going down. Because these cancel out, we say that the molecule is non-polar. Typically when a molecule doesn't have a lone pair, it tends to be non-polar, despite the fact the molecule itself contains polar covalent bonds. There's a difference between a bond and a molecule. The molecule itself is non-polar, despite the fact it contains polar covalent bonds, right? Very good. So I've covered all the basic examples for electron pair geometry. You can continue growing. You can just pick any compound from the homework or anywhere and try it. You most likely will have no problems. So in week 5, we're going to talk about molecular geometry, and that can get a little tricky. All right, so stay tuned for week 5 videos on molecular geometry, and that's it for week 4 on electron pair geometry. All right, okay, bye bye.